Hi, everybody. As Barbara said, I'm Silvia Bertoli. I'm a postdoc at INAF Padova, and I'm a planetary geologist. And during my PhD and also in my postdoc, I study permanently shadowy regions on Mercury's poles. But what are permanently shadowy regions? So the permanently shadowy regions are sectors of a surface of airless planet in general, associated with craters, depression, fault scarps, so topographic features on the surface of airless body that are never directly reached by solar flux. So this is very interesting because if they never reach by solar flux, these regions reach a very low temperature. This is caused by the rotation axis obliquity, which, for example, is equal to about 2 arcminute for Mercury. So in the North Pole and in the South Pole, a lot of craters and depressions have these regions, and the temperature is very low. So it is interesting because if you understand, we are in the airless body, but with this incredibly low temperature, so could be possible that ice could be deposited in these regions. And this is the idea of scientists in the 60s. And this is where is began the tales of this ice discovery, because in the 1971, there is the first theoretical predictions of ice in these permanently shadowy regions on Mercury, because they're supposed to be very similar of those on the moon, because also on the moon we have these permanently shadowy regions at pole and we have water ice. So they start to think about it as a theoretical point of view, and then we have the first discovery of water ice in these permanently shadowy regions with the Earth-based radar analysis, which have this kind of data. We in these pictures we are in the North Pole of Mercury. Those are the craters, and the bright features is the water ice, or what is supposed to be water ice, because at the beginning they say, okay, we have discovered something which are very bright, but we have to connect it to something. We know that water have a specific radar reflectivity, so they compare this radar reflectivity of Mercury permanently shadowy region with those, for example, of icy satellites, or also with those of the moon. But they need more detail, more proof about the presence of this water ice. And the other proof of this water ice was made with a messenger mission. The messenger mission was a mission that arrived on Mercury and stayed there in orbit from 2011 to 2013, and take a lot of data of the planet, and in particular in the North Pole, they measure a lot of hydrogen content in this permanently shadowy region, and where the water ice is supposed to be. So they start to connect all the stuff. So the reflectivity, the presence of this hydrogen, but also the temperature, because we know that there are permanently shadowy regions, but we need some proof of the persistence of this low temperature in these permanently shadowy regions. So all the models that are made in the pole, North Pole and South Pole of Mercury, are in the thesis that ice could survive and could be deposited in a billion years in these permanently shadowy regions that I say PSR, so it's it's easier to repeat. So with the Arecibo radar water ice reflection, that were the first initial data that we had for the permanently shadowy region for the water ice presence. Then we have the messenger mosaic, and then we have also the shadow and the temperature, and so all the modeling about to prove the presence and the survival of the water ice. We have the discovery on Mercury. There is ice. There is ice in different kind of situation, because we have some craters that present permanently shadowy regions and also rather bright material. So what we expect, water ice accumulate and deposit in these permanently shadowy regions. But we have also some regions that you can see here in pink that are rather bright only. So there is a lot of water ice, but no permanently shadowy regions, which is very particular. And also we have some places that are permanent shadowed only. So the radar couldn't detect radar pregnant material inside the yellow spots that could be connected with kind of limited views, for example, of the radar in the detection of radar pregnant material in this region, but could be other reason. There are a lot of mysteries linked to these permanently shadowy regions. Now let's have a look inside the PSR because, okay, I say that PSR are are permanently shadowy region and impermanently shadow for billions years. But in fact, Messenger had some pictures and images of these regions because, of course, in craters, for example, we have some photons that could reach this part of the crater and could illuminate a little bit also these shadowy regions. So, for example, here we have Coffee craters, which is a very big crater, 150 kilometers of in diameters, and we have here the inside of craters. And here in the lower part of the crater, you can see there's some bright. Oh, sorry, there are some bright deposits that you could see. And this could be ice exposed in the surface. Here, for example, another example is Yoshikawa crater, and here the permanently shadowy region that we see very well. And also here the surface appear kind of bright, you know. And here we have also Fuller crater. We have the shadowy regions, and here the image of the inside, which is very useful for us because we can study the geology, the geomorphology, and the topographic features that we can see in the surface, and we can, of course, compare with the presence of water ice, and you can make some analysis of that. But okay, we have ice on Mercury, but which is the origin of this ice? Because it's accumulated in billion years, okay, but where it comes from? So there are three theories in general associated with the origins of the water ice that could be deposited in these permanently shadowy regions. The first is exogenic processes. So all the ices that is carried from the outer to inner solar system by comets, asteroids, and micrometeorites impacting on Mercury's surface that could bring a lot of ice that could accumulate is in this PSR. One of the most important candidate impactor that could have bring a lot of water ice, specifically in the North Pole of Mercury, is Hokusai crater. You can see here the impact of the crater and the ray, and they think that with in an airless body as Mercury could be this process, which is called migration. So ice at the time of the impact could evaporate and form this transient exosphere around Mercury planet that could migrate at the North Pole, and then at the temperature of the North Pole could condensate and deposited in these permanently shadowy regions. And so this is why those kind of craters was associated with all this material in the North Pole, because in fact the impact is not so high in latitude. So in an airless body, it could be strange that it could be yeah, could be the best candidate. But yes, with this process like migration, could be one of the best candidate, but also the impact that happens directly at the North Pole and directly at the permanently shadowy regions. A second theory about the origins of the ice could be the endogenetic process. So the polar ice are formed by condensation of volatiles in cold trap during intense volcanic outgassing events. So, for example, the outgassing events that form the smooth plain in the north, or during the possible development of a global magma ocean. But this theory is the less considered when we consider the origin of the ice in general on Mercury. Then we have the solar implantation. The solar implantation, which is the same system that deposited water ice on the surface of the moon. In practical, the water could be thermally synthesized from OH bound to mineral species through the implantation of solar wind protons. So is the interaction between the solar wind with the regolith that create oxygen, hydrogen, which could connect and form water ice. This is a good theory, but is and could be could have bring a lot of water ice in the surface of Mercury, but is like pure ice. And they found that the water ice which accumulate in the PSR are not so pure, but mix with carbonaceous material. And carbonaceous material usually is bring by micrometeorites or asteroids or comets. So it's okay, could have bring some water ice, but it's not the most considered. And so this is asking about the formation of this water ice, just to say how this water ice could appear in these permanently shadowy regions. Because if we fall to water ice, okay, we can fall to a glacier, to, you know, how it appears, this water ice in this permanently shadowy region. So we have the craters with its shadow part, you can see here. Then arrives a body. Here we consider the theory of exogenetic process. So arrives a comets, and these comets leaves a lot of water ice in the craters. And you see that the water ice, okay, accumulates in the part of the shadow because of the temperature, and melt and evaporates in all other part of the craters. And with time, we have also the evaporation of some of the water ice deposits in the PSR, and the deposition of this black material that you can see below the water ice. And this is what is called the low reflectance materials, or low reflectance materials, because looking in deep in this permanently shadowy region, we see, okay, bright regions, but also some dark region associated with these bright regions. So we thought that below this water ice could be this material, this very thin layer of carbonaceous material that works as isolated material for the ice, and so could keep the water ice safe, and water ice could stay for billion years in the permanently shadowy regions. And so we can fall to this water ice in PSR like an alternation of layers of water ice, and then this low reflectance material, so carbonaceous material, and then water ice. Okay. So for now, we have the data from Messenger, but en route to Mercury, there is Bepi Colombo. And Bepi Colombo will provide the best understanding of Mercury to date, because we have a specific instrument, which is symbiosis, that could be very useful for the detection, mapping, also the retrieval of a composition of volatile species on PSR, because what are missing about the all these ice deposits in the water ice, which is the composition, which could be very important in order to associate the water ice to a specific body, comets or asteroids, of the type of asteroids, of course, and have a lot of more images, and detailed image of the surface could help us a lot. But in the meantime, while we waiting for Bepi Colombo, what can we do? Just a little pictures of one of the last flyby of Bepi Colombo around Mercury. And in the last flyby, Bepi Colombo took a pictures of the permanently shadowy regions that you can see here. A lot of craters that are completely in shadow, and some so, which is very interesting pictures. And but while we're waiting for Bepi Colombo, what can we do? we can map the PSR. Of course, you are in a mapping school, so you can map the surface of Mercury, and also you can map the PSR. This is part of my work of a PhD thesis, and it is very important because if we mapping the PSR, the permanently shadowed regions in general, we can have a geomorphological, a geological point of view of the craters, of the deposits of the craters, and how the deposit, the ice deposits, and in general deposits of the crater have a relationship, and understand if ice could have some could modify the surface, because of course we have the ice below the surface, below these low reflectance materials. So how the reflectance materials answer to the presence of this water ice in the subsurface, and how the shape also of the crater could be different for the presence of this water ice at the moment of the impact. Okay, so if we do map of this PSR, we can understand something about the stratification of the craters and the relationship between the presence of the water ice and also the modification of the surface in general. And of course, we can also via mapping, because we can also detect all the craters on the ejecta or also on the floor. We can also dating the surface, because we know that more craters we have in the surface, more the surface could be older. So following this very simplified thesis, we can understand we can say something about the origin of ice, because we put some absolute or almost relative ages for the icy presence, and we can say, okay, it could be connected, for example, with Okusai impact crater, or could be say if water ice could in fact modify the floor of the craters, and we have some modification and some relationship with the topographic of craters in general. So this is, for example, connected with the same crater here of the mapping. And we see that in green, we have the ejecta of the crater, so the time of the impact of the crater. And in red, we have the part of the craters here that is not covered by water ice, but is probably in the past modified by this water ice, and is very younger respect to the ejecta, and seems not modified from all over some genetic process, no landslide, no process, so could be connected with the presence of the water ice in this PSR. And this is very interesting. And the blue part, which is the part of the floor that is covered by this water ice, and this is in the very in the very PSR of this crater, is have a very few craters, so seem really young. So this is very important, and this is a point of this rejuvenation of the floor of the craters, and so could be a key to understand this modification and this relationship between, of course, the presence of this water ice and the modification of the surface of craters. And with this, I have finished. It was very short, and yeah, if there's some questions, I'm here.